So in this section we're having a look at infinite geometric series, and a reminder that an infinite geometric series is when we add up all of the terms of a geometric series. In fact, when we add up to n equals infinity or n approaches infinity. And the size of r determines what happens. If we've got an r that's bigger than 1 or less than -1, if we add up all of the terms, if we add the first 10 terms, we end up getting a large positive number or a large negative number. And then if we add up the first 100 terms, you can see that suddenly we've got a massive number, 5.36 by 10 to the 59, or a very large negative number, -3.21 by 10 to the 59. So both of which are very large numbers. And I hope that you can see that if you keep increasing the size of the terms, the more terms you add up, the bigger the sum is going to get. And in actual fact, we end up approaching infinity. If we add up infinity terms, we end up approaching a sum which is infinity, because this means that the terms are getting bigger, either positive or negative, but they're getting bigger each time, each successive term. On the second set of examples, we've got a ratio of a quarter, which means each term is getting smaller than the first one. And you can see it over here. We've got 1, a quarter, a 16th, a 64th. Every time that denominator increases, the term is getting smaller and smaller. So now, instead of adding something that's bigger and bigger each time, we're actually adding something that is smaller and smaller each time. And what happens is, if we do 10 terms, we end up with a small positive number. If we add up 100 terms, we end up at virtually the same very small positive number. It's not until we get out to these last 3 decimals that we see a difference. Same if it's negative. It's because it's between -1 and +1. So even when it's negative a quarter, if we take the first 10 terms, we end up with 0.7999924. We take 100 terms, then we've got virtually the same positive number. That means we've added 90 more terms and there's been virtually no change to the sum, because we are adding smaller and smaller and smaller and smaller amounts each time. And it's all to do with the size of r, and that's this little symbol here. So it's sometimes known as the absolute value of r, or the modulus is another word. Modulus. Oh, I can't spell. Modulus, I think. Maybe there's an O in here. So it's called the modulus, or the absolute value of r. And we can see that, like in this little bit here, that it's between, r is between -1 and 1. When r is between -1 and 1, if we raise it to the power of increasingly large numbers, what we see is r to the power of n becomes smaller and smaller and smaller. Okay, so now we're talking about an extremely small decimal. We've got to move the decimal point 7 places to the left, or 61 places to the left, or 91 places to the left. Eventually, if we put it into our calculator, a quarter to the power of 200, it will tell us that it's 0. But we should be careful to recognize that it's not actually 0. It just means the calculator can't calculate anymore, so it just says, I give up, it's 0. The important thing is what happens when that r to the power of n approaches 0, what it does in our general sum formula. So this is just the general sum for a geometric series, which has got r to the n in it. If that r to the n is approaching 0, then our sum is going to approach t1 outside of 1 minus 0, because rn is approaching 0, over 1 minus r, which means it's going to approach t1, because 1 minus 0 is 1, 1 times t1 is 1, over 1 minus t1 over 1 minus r. And that's the rule that we're using. We don't use the approaches symbol, we just use the equals symbol. And so, like I said when I gave you this sheet, the important part that you need is in the box. So if the absolute value of r, or the size of r, is less than 1, as in it's between -1 and 1, an infinite geometric series of the form Tn AR to the n minus 1 will converge, which means, quite specifically, get closer and closer to, but not actually reach, the sum of this. And so this is the formula that we're using, and it's called the limiting sum. All right, in the next example, we'll work out how to write 0.8 recurring as a rational number.